Welcome to the course on two-dimensional signal processing, principles and practices. As we have completed the signal processing overview for 1D signals, we will also look at the 2D signals, and it's the recap of the previous 1D signals. In the recap, we have done a 1D signal, the signal definitions and its classification, different types of signals, and the basic signal models also we discussed, and the signal models in continuous time and in the discrete time, and then overview of the sampling, the sampling process, how it is helping to get the discrete sequences, for how do you fix the sampling frequency for a particular signal. And we will also explore this sampling, 1D sampling in detail with the spectrum, and the how do we filter it to get the base spectrum only, on all these details in the coming lectures. We have also done the signal operations on continuous and discrete time cases, where shifting and the scaling, what is the order of preference we have to do, or if you change the order, what is the thing to be taken care. So these signal operations on continuous time and discrete time we had discussed. Also, the discrete time system is introduced with some examples, and the very popular and common discretized systems we had look into, that like moving averager, accumulator system, and so on. And also the properties of them, whether it is linear or time invariant, those details, and the system response, especially when we consider this, it contains the two components, that is zero initial conditions, what is the response, that means zero state response, and then the case of the input, when the input is absent, that is the zero input response. So zero state response and zero input responses we had seen. And the system also, its classification. So we define the system and its classification, different types of systems like LTA system, also the causal and non-causal invertible systems, also the stability of the system, those we have done. And then the LCCDE, linear constant coefficient difference equations obeyed by the discrete time systems. How do we solve that? We saw with one example, and through the LCCDE, how do you get the zero input response and the zero state response, and what is the total solution, and how this homogeneous solution and the particular solution helps in getting the total solution, and how these homogeneous and particular solution are related to the zero input and zero state responses we had seen. So the total response, which contains both, and then the convolution sum we had seen, and what is the importance of convolution sum. If we know the impulse response of a particular system, and then we can get the response of that system for any arbitrary input, so that is through the convolution sum we had discussed also. So with this background, the remaining one-dimensional algorithms or the analysis, like Fourier transform for 1D and all those things, when we do the 2D, and we'll also first look at the 1D Fourier and analysis, and then we extend that 1D Fourier analysis to the 2D. Similarly, the Z transform, 1D Z transform, and then we extend that to 2D Z transform. So we will see them then and there when we discuss the 2D systems. And now coming to the 2D signals, in which that what is that 2D signal. So this whole course is about these 2D signals, and how do we process it, and what are the algorithms of 1D can be extended to 2D, and all of these things we discuss. So now we get into the basic 2D signal definition. So 2D, we restrict here to this discrete one, because we are going to DSP processing we are going to do. So this is fully, hereafter we will be talking only about the discrete sequences. So 2D discrete space signal, or the 2D signal, a 2D discrete signal we can say, or a sequence also, is represented by a function. So this function will have two arguments or two independent variables, as I said, as we defined also in the case of the definition of the signal dimension. It is going to be a one-dimensional if it is depending on only one independent variable is there. If it is having the signal having two independent variables, then a function which is having the two independent variables, then it is going to be a 2D signal. So here the two independent variables we will have, and those are integers only, because it is a discrete 2D discrete signal. So the The signal generally, for example, this x of n1 comma n2, so within the square bracket we'll use for the discrete case. So the n1 is one independent variable and n2 is the another independent variable, and these n1 and n2 are all integers in this case. So x is function of n1 and n2 here, and this is for it is x of n1 n2 for a non-integer n1 n2, that is n1 or n1 is 0 1 2 3 4 integer values. It is defined, x of n1 comma n2 is defined when this is not non integer. In that case it is not integer, then those values are not 0. We should not assume that when n equal to between 0 and 1 it is 0. So it is not the case, so it's not 0 but it is undefined. So those instances this signal sequence is not defined. And example, the image which I have given you, 3-bit image, suppose it has an intensity the pixel value at x equal to 1 and y equal to 1, or x equal to 2 and y equal to 2, or x equal to 1 and y is 2, 1 comma 2. So different pixel values depends on this. It is the x and y, what we are saying was the independent variable in the case of image example we took. And now coming to the sequences, the basic sequences, what we had seen in the 1D cases, the basic models, if you recall, then we will extend those basic models, signal models, to the 2D as well. So the first case we take the impulse sequence, that is 1D unit impulse. We all know already it is a unit sample sequence which is always represented by delta of n, and it is defined as delta f and is defined only at n equal to 0. This is 1 because it is unit impulse, or it can be of any value if it is simply an impulse, and it is 0 otherwise. All other instances it is not, it is 0. So this impulse, we know the n is varying here, 0 to 0 this way, it is minus infinity to plus infinity, n can vary, but n can take only the integer value, and n equal to 0 it is defined, that is the impulse sequence. This is 1D, one dimensional sequence which is defined only at n equal to 0, and other instance it is 0. Now taking the 2D signals, so we extend that 1D impulse, and now we look at what is the 2D impulse, 2D unit impulse, especially the amplitude is 1, then how does it look like? So this is also an impulse or unit sample sequence which is represented by del of n1 comma n2. So here we should take this, there are two independent variables, the n1 comma n2, it is defined as here del of n1 comma n2 is 1 when n1 and n2 equal to 0, it is 0 otherwise. So this the integers n1 and n2 are 0, then this sequence has a value 1, otherwise it is 0. How do we picturize this in a plot? So when we take in the 2D, the x-axis is n1 and for the y-axis is n2. So we this x and y, it can be an x and y as well. So because we have this time instance usually in the sequences, so we just taken the notation as n1 and n2, and when n1 is 0 and n2 is 0, this is the point, and we can visualize this actually as an impulse which is at n1 and n2 are equal to 0. And when we look at this, so this would be looking like a point. Okay, so this is what the circle, which is a small circle, or the point which is shown over here in a different color, that's amplitude of it is 1. So this is the way in which we represent the 2D impulse sequence, and its amplitude is 1, which is always represented with the bracket. What is the value it takes? It is 1 at this point and 0 everywhere, and 0, so it does not show that those things. So this is the representation of the del of n1 comma n2 2D impulse, which is unit impulse here. So the equation or the expression of this 2D impulse is this one, del of n1 comma n2 is 1 when n1 and n2 both are equal to 0. Now coming to the 2D unit impulse itself, how do you visualize in 3 parameters? We have this 3D here, that is n1 is one x-axis and n2 is another, that is y-axis, and the value 1, which is del of n1 comma n2 is 1, is you can see that at n1 equal to 0 and n2 equal to 0, this is unit amplitude. So this is actually the case of 1, which is given over here. This is a unit impulse. Okay, so we can visualize this when we look at in the top view. This is only showing that the point, it would look like a point. That point is only represented in the previous diagram. So now this 2D impulse, whether it is separable or not. So the separability concept will help us to make the analysis easy in the two-dimensional signal processing. So what is the meaning of separability here? We will introduce that separability, and we will use this separability also, the property of this 2D signals, in some of the analysis. So when the unit impulse is separable, meaning that is del of n1 comma n2 can be written as del of n1 into del of n2. So the multiplication of two sequences, one sequence is with respect to n1 and the other sequence, this is with respect to n2. So if we are able to split a two-dimensional sequence into two one-dimensional sequences of n1 and n2, here del of n1 and del of n2, then that function is separable. This is also valid for n-dimensional. So here we are just discussing two-dimensional, so del of n1 and del of n2. So how these impulses would look like, that is del of n1 and del of n2. Okay, so we'll see them, that now the 2D unit impulse is, this can be separated, or it can be written in as a multiplication of two 1D impulses. Now coming to the line impulse, what are the different cases of impulses we have in the 2D case? So vertical line impulse is one. The vertical line impulse, which is represented by del suffix t, here t is the representation just to differentiate it from the 1D notations, t and n1, which is defined as, this is del t n1, that is the one which we had seen the previous case also, x of n1 comma n2, which is equal to del t of n1, which is equal to 1 for n equal to 0, n1, that is n1 equal to 0 here. It is 0 for other values, that is other values of everything with n2 and other things, it is 0. So how this impulse would look like? So it is n1, when n1 is 0, this becomes 1 in two-dimensional space, but how we are going to see this impulses? So this axis, we said this is n1 and this is n2, and this notations we use it throughout this course, and for when we deal with images, that this maybe we will interchange, but right now we would understand with this n1 is this, and then n2 is the y-axis. Now del t of n1 that is equal to 1 value, 1 here. So for n1 equal to 0. So this n1, all the values of n1 0. I mean n1 0 is this point, and then n2 can take any value. N2 can be 0. This is n1 is 0 and n2 is 1 here. N1 is 0 and n2 is 2 and n2 is 3 and so on. And similarly here n1 is 0 and n2 is here having this -1, -2, n2 and -3 here. So n2 can take in this delta of n1 comma n2, in that n2 can take any value from -infinity to +infinity, but n1 is 0. So that is the impulse. This is called an impulse, which is del t of n1. So we can have this del of n1 comma n2 as one impulse this way, that is a vertical line impulse, as we had given in the separability concept, del of n1 and del of n2. So this is del of n1, so it's a vertical impulse shown over here. N2 can take any value, but n1 will be 0. And if we take the horizontal line impulse, so the one which we had seen is the del of n1 is vertical impulse, and then horizontal line impulse, which is represented by del t of n2. This is obeying the equation that L of n1 comma n2 is del t and n2, and which is 1 for n2 equal to 0. So the n2 is 0 and n1 can take any other values. So if it visualize this in the picture, that you can see n2 is 0 for all the cases, but n1 can take any value from -infinity to +infinity. That is, n1 is 1 here, 2 here, 3 here, and so on. It will continue. Similarly, this side it is -1, -2 and -3 and so on. So it can take any value, n1 can take any. So this is del t of n2, where n2 is going to be 0, then it is 1, otherwise the n1 can be of for all other n1 values. So this is an horizontal impulse. So we can get this del of n1 comma n2, the two-dimensional case which we had seen there, del of n1 comma n2, we separated into del of n1, that is vertical impulse, and the horizontal impulse. So if you multiply the two, if you remember, this is the point which is common to both. Okay, so the del of n1 and del of n2, which is resulting in del of n1 comma n2. That is the very first the impulse, that is 2D impulse we had introduced. So we have it in 2D, we don't have only one impulse, we can have this 2D impulse and the horizontal line impulse and vertical line impulse as well. So these are the line impulses which are used in the two-dimensional signals. So diagonal line impulses, the other category, which is also called the diagonal impulses. The diagonal line impulse are defined as here, x of n1 comma n2 is del t, this just to differentiate is this t, n1 plus n2 equal to 1. That means this is valid only when n1 plus n2 equal to 0, this impulse. Okay, so n1 plus n2 equal to 0, when we say what are all the values in which this is becoming 1. So n1 equal to minus n2 or n2 equal to minus n1, all these values, this signal would exist. That means to visualize it here, this is n1 and n2 axis, then here n1 equal to, in this case n1 0 and n2 0 is also, this equation is valid. So here we get this point when both are 0 and n1 equal to 1, then n2, what is the minus value of something, here is this n1 1 and n2 is minus 1. So in this case, and then n1 2 and then n2 is 2, so that is minus 2. The slope is negative here. So this is passing through the origin with the slope minus 1. So this is the diagonal line impulse. This is called a diagonal line impulse with the slope minus 1 here. So and similarly in the other side also, you can see that this negative slope is valid. Here it is n2 1 and n1 is minus 1 and then minus 2 and n2 plus 2 and so on. So this is the diagonal line impulse. And this is the third category. And the diagonal line impulse, it's not only having the slope equal to minus 1. So it can have the slope which is plus 1 also, that slope. So it's going to be the x of n1 comma n2. This is the two-dimensional signal which we are defining, where del t2 which is going to, t is again just for different cases, we are saying the second category of this diagonal line impulse. n1 minus n2, it's equal to 1. So that is the index n1 minus n2 should be 0 for this should be this del of 1 to 1. So n1 minus n2, make it 0 and get this, what is the relation between n1 and n2, for which the signal exists. So n1 equal to n2, those values only this signal they would have one value. So if you plot them, that is n1 and n2 here, n1 equal to 0, this would be equal to 0, and n1 1 and this is also 1. So you get this equal to values, which is equal to n1 equal to 1, n2 1, n2 2 and n1 1. So these are the values, equal values for which it is that is also valid for negative indices. This is minus n1 minus n2 in the sense minus 1 and minus 1. And so all n1 n2 values, this is valid. So the diagonal impulse is this way, the slope is 1 here. So what should be the amplitude of all these things? These are all ones here. Okay, these are all 1. Similarly, in the previous case also, we have these values are 1. All of them is going to be 1 here. So this is another diagonal line impulse, and we move on to this, how do we find the slope of this line impulses? So here we can represent that as delta of p n1 plus q n2. So n1 can have some integer multiplication here and n2 will have the integer multiplication of this. So here where p and q are the integers, it won't take the real values here, it would be the integer values. So where the slope of this integral is p n1 plus q n2 equal to 0. So we have to equate it to 0 to have the impulse value 1. So p n1 plus q n2 equal to 0. So p n1 equal to minus q n2 and p by q or the y by x, this is n2 by n1 is equal to minus p by q. So negative of this p by q ratio, there it gives the slope of this. So whatever the p and q integer values would be, the slope would be accordingly shift. It is a high slope or the low slope, the diagonal impulse would be in that way. So what we had taken here is p and q were 1 in the previous examples what we had done in the two cases. So now this It's not, if it is not 1, and you will have a definite slope in that. So this is how you can compute the slope of the sequences. So let's see how do we plot some of the sequences with the knowledge what we have right now with the impulses. Can we plot a second, that is two-dimensional sequence? So for sketching the x of n1 comma n2, del of, for it's equal to here del of n1 minus 2 comma n2 minus 3. That is, you can see the index n1 is shifted with 2 and n2 is shifted 3. That is right shift, the n1 minus 2 and n2 minus 3. So this sequence is also having del of n1 minus 1 and n2 minus 1. This is also delayed or shifted, one delay in this n1 index and another delay in this case of n2 index as well. So now we have to plot the two different sequences and then add them together to get this x of n1 n2 and visualize how this would be. So if we add the first one, that if we just plotted the first one, del of n1 minus 2 and n2 minus 3. So del of n sequence is actually del 1 n1 comma n2 is valid at only the origin, right? This is only origin, the n1 and n2 valid only at this point, right? So now if we are shifting this to del of n1 minus n1 minus 2, in that case it is shifting here in this direction 2 and n2 minus 3, that means n2 3 shifts here. So that impulse would be available only at this point, that is having the unit amplitude 1 here. So this is 2 comma 3, two shifts in the n1 direction and 3 shifts in the n2 direction. So this is the first signal which is having the first components this signal has. And let's look at the similarly the second one. This is also an impulse where the n1 is shifted once and n2 is also shifted once. So here n1 1 and n2 1. So this is the signal where this is only having this one impulse, and now adding this 2. So adding this 2 in n1 and n2 plane, that what we have in the 2D signal, this would be available, and in all other places or the values of n1 and n2 it is 0, and here also it is 0 except this point, and similarly here this. So when we add these two, we would have only these 2 points as the summation of x of n1 comma n2. So let's see that here this is the one which is contributed by this signal, and this is the one which is contributed by this signal. So these two of them added together is the x of n1 comma n2. So it's just a plotting of the sequence. So now we move on to the step sequence after learning that impulse sequence. So 1D unit step, we had already know what is the unit step sequence, that u of n is equal to 1 for n greater than or equal to 0. So the u of n, which is defined as 1 n greater than or equal to 0. So when we plot this, it is a sum of impulses, shifted impulses, as we had learned in the previous, x of n can be of written in any arbitrary sequence, can be written in terms of the sum of shifted impulses with the amplitudes as of course. This is unit 1 here, and it is this is u of n. This is a step signal. This is valid for 0 to infinity. So that is n greater than or equal to 0. It is 1. So this is one dimensional step sequence. So how this one dimensional step sequence can be visualized, or it can, or how the 2D step sequence can be. So this 2D step sequence is defined or represented by u of n1 comma n2. So it's not only n, 2 independent variables, and u of n1 comma n2 is equal to 1 for n1 and n2 greater than or equal to 0, and it is 0 otherwise. So these are so n1 and n2 0 onwards, if greater than 1, that means that is the first quadrant, right? So we will see the sequence how it is to be plotted. That is n1 varying and n2 varying in this direction. So what is the signal? n1 varies, it is 1, and n2, this is for n2 0 and n2 has some values, and similarly this is for n1 0 and n1 has some values, all of them. So u of n1 comma n2 is extended up to infinity here and infinity here, but it is absent in the second and third and fourth quadrants, all of them it is absent. So it is only in the, because n1 and n2 are greater than or equal to 0, it's only these values, n2 greater than equal to 0 and n1 greater than or equal to 0. This is valid only in the first quadrant. So, the 2D step sequence should be visualized this way, and all these points are having the value 1. So, this is just representing the n1 and comma n2 is 0, it is not the value of this. So, these values would be 1, all of them would be 1, the amplitude will be 1 for this. So, now if you visualize this in 3-dimensional way, 3D picture, the n1 is this axis and n2 is in this axis, and u of n1 comma n2 takes one value 1, that is from here, and here you can see this is having the value 1 everywhere. With the discrete points, that is a top view of this is actually the what we are looking at here. So, this is 0 in the other quadrants, like in these spaces it is 0. So, this is just a visualization of the 2D step sequence. Now, this 2D step sequence is separable or not. If it is separable, then we are able to write it in terms of u of n comma n2 equal to u of n1 into u of n2. So, is it possible to write it? If it is so, then this is separable. So, let us see that what is u of n1 and what is u of n2. The step sequence itself having the two different cases, and this separability, which is the x of n1 n2, as I said, it is separable if it can be expressed as x1 of n1 and x2 of n2. That means the x of n1 comma n2 in terms of two sequences. Let us see this is the case of only 2-dimensional. If it is m dimensional, this can be extended to n dimensional or m dimensional also. In that case, you have x has many independent variables, or it is a function of many arguments n1, n2, n3 and tnm, which is equal to the product of I is varying from 1 to m. Now, how many dimensions we have? For example, 2, I equal to 1 and 2, xi, ni. So, this x suffix I, this is x1 and ni is 1. So, this is x1 n1 and x2 n2 can be represented in terms of x1 and n1 and into x1 x2 n2. So, if it is if it is expressible in this way, the signal x of n1 comma n2 or any dimension, it is a product of multiple dimension m whatever the number of arguments we have, then the sequence is separable, this sequence is separable and this sequence is separable. So, this is the concept of separability. So, in the case of images x of n1 comma n2, there are 2-dimensional only. We have seen this example like in the signal processing overview of 1D signals, x of n1 comma n2 comma n3, then the video that is having the not only x and y, the space coordinates or the space variables, it is also having the time. So, the image frame is taken for every time instance. So, that is the 3-dimension here. So, it is easy to handle if it is separable, that 2D signals or the 3D signals can be very easily analyzed through this separability concept by using the one-dimensional analysis, whatever the Fourier analysis or the convolution and everything can be easily used for 2-dimensional signals if that signal is separable. Image or video is separable, it is applicable to this. The signal processing techniques will be easy. 1D signal processing techniques can be used for the 2D and 3D things if it is separable. And some of the special functions or the specific functions also would see in this case. So, x of n1 comma n2 is ut n1. So, we have seen that u of n1 comma n2 can be separated into ut of n1 and ut of n2. And so, what is the meaning of this? It is equal to 1, this function is equal to 1 for n1 greater than or equal to 0. So, this all values of n1 which is greater than or equal to 0, this is 1 in the sense if what it is 0 for other values, so it is 0. So, like a step sequence. So, what does it mean n1 greater than or equal to 0? So, that means n1 here is taking only the positive values, not the negative ones. So, negative ones of n1 is not allowed, but n2 can take both, that is positive and negative. This step sequence is extended in the both the directions of n2, but not n1. Okay, so n1 is having only one direction, this is u of n1. Okay, so this is the step sequence of the signal which is ut of n1. So, what should be the sequence similarly for ut of n2? Okay, so the ut of n2 is x of n1 comma n2 is equal to 1 for n2 greater than or equal to 0. That means it is 0, otherwise in that case n2 should be at greater than or equal to 0. N2 cannot take negative values, but n1 can take negative values. So in that case, how the signal would look like? So ut of n2 is n2 here absent, that is, it is this values cannot take less the negative values of n2, but n1 can take both the values positive and negative. So the step sequence would be spreading across the first and second quadrant. So in the case of the previous one, it spread across the first and fourth quadrant. Okay, so this is n2 ut of n2. So if we multiply these two sequences, the first one and the one which we had seen here, this and the sequence of this second one, so the in this first quadrant is common, so up to this is common, so you would have the sequence, you will get the step sequence, two-dimensional step sequence in it. So it is possible to get the step sequence, 2D step sequence from both of that. So it is separable sequence. Now we will take some example of the step sequences and how do we plot that and what is the shifting, what we learned in 1D, right shift and left shift can be applicable here. How do we apply it here as well? So sketch a sequence, for example x of n1 comma n2 is having the step sequence u of n1 comma n2, this is only in the first quadrant, and minus u of n1 minus 3 comma n2. So we would separately plot this and subtract this one from the first one. In that case, so u of n1 comma n2, this is the step sequence u of n1 comma n2 in which you can see that it is in the first quadrant. So it is extended to n1 infinity and n2 infinity, but not the other side, the values of n1, that is negative, and this negative values are not allowed here. So this is a 2D step sequence. And what about this sequence? So here this n1 is only shifted to minus 3. So in that case, this signal is shifted here, right, shifted up to here. So it is below 3, it is 0, and it exists from 3 to infinity of n1, and similarly here as well n2 from 0 to infinity. So this is the sequence of u of n1 minus 3 comma n2. So now subtract this sequence from the one u of n1 comma n2. So if we subtract it, what should be the sequence? So from here you have 1, these are all values 1, here these values are 1, isn't it? So similarly these values are 1. The 3 does not represent the amplitude, it is representing n1 here, 1 and 1, all these values are 1, and if you subtract this 2, what we get here is this 1 minus 0, it is again 1, and here as well you would get, and then 2 here, and at 3 this minus this becomes 0. So from n1 equal to 3 onwards it would be 0. So the x of n1 comma n2, because of the minus sign, so this minus this would represent the n1 n2 here. Here 0, this is the sequence 0 1 2 of n1, and we have all the values of n2 equal to here, similarly n2 going to infinity, this will be extended to infinity. So the sketch of this sequence is x of n1 comma n2 is this. So the step sequence, a sequence with sum of or subtraction of step sequences, shifted step sequence can be represented like this. Now see that whether sketch u of n1 comma n2, check if this function is separable or not. So whether it is separable or not, I said this is going to be u of n1 comma n2, and u of n1, what is the sequence? N1 equal to n1 greater than or equal to 0, it is existing. U of n2 is n2 greater than or equal to 0, that is existing. So we will see the two step sequences, that is u of n1 comma n2, where n2 can take the values, and this is u of n1. And as we said that in the previous example, this u of n2, which is here taking the n1 both the values, and n2 is only greater than or equal to 0. So if we multiply these two, yes, definitely we can get this u of n1 comma n2. So see here, this portion is common when we multiply the two. So this portion here it is there some values, but here it is absent, and this quadrant is absent, so this there is no values here, and this quadrant is absent, and this if you multiply this would give 0. So multiplying these two sequences would result in u of n1 comma n2. So u of n1 comma n2 is separable. So this can be expressed in multiplication of this, and this function is separable here. So what we had learnt in the case of 2D signals, had the recap of the 1D signal processing, that overview of it, and then we extend those things what we had learned to 2D, and we have just seen the basic signals, that is 2D basic signals like the impulse and the step sequences, both 1D and 2D, and how is what we have also learnt the separability concept. How do we apply this separability concept in a 2D sequences? If the sequence is going to be summation of impulse or the step, can we represent that sequence as a separable sequence? That would help in analysis. So we just learned the separability theorem. For how do we extend that theorem, which is also for n dimensional sequences it is valid. So we'll continue with this many of the 2D signals, like the exponential sequences of the basic signal models what we had done in the 1D signal processing with the two dimensional exponential sequences. So we'll do the exponential sequence and the rest of the things in the next lecture. Thank you.